In this video, we show you the functions for machine monitoring on the VM80 and VM100 analyzers. The handy instruments are operated in a simple and intuitive way via touch screen. The machine monitoring functions can be activated by purchasing a software license. This license includes 3 modules: the actual machine monitoring module for route-based measurement, the envelope analysis module, and the amplitude over RPM plotter. We begin with the route-based machine monitoring module. The measurement route table is initially empty. We will now add the first route point. The analyzers have a read function for NFC tags. These are inexpensive and robust, contactless memories that contain a unique serial number. It is read by the analyzer as soon as it is brought within approximately 5 centimeters of the NFC tag. NFC tags are used for the automatic identification of measuring points, which greatly simplifies route measurement. No additional data is stored on the NFC tag. If automatic identification is not required, a measuring point can also be created by pressing the plus button. In this example, we create a new route point using an NFC tag. The input mask for the new measuring point appears. First, fill in some text fields for a description. In this menu, you choose what type of monitoring is to be applied. First, overall value monitoring based on RMS or peak values. This type of monitoring is suitable, for example, for unbalance. Or, second, uniaxial roller bearing monitoring. Since the module has 3 measurement channels, the input or sensor axis can be selected. We choose overall value monitoring with RMS values. By selecting the integration, you decide whether vibration displacement, velocity, or acceleration is measured. High-pass and low-pass filters are selectable. Limit values for warnings and alarms must be entered. If you are unsure which settings are correct for the machine to be monitored, the device offers an assistance function. This includes various ISO standards for vibration monitoring. You are guided step by step through machine-specific options to finally obtain the appropriate settings for measurement as well as warning and alarm limit values. After closing the standards wizard, the settings are applied to the route point. Now you need to specify how many days apart measurements should be taken. In some cases, it may also be useful to record the rotational speed. This can be done, for example, using the optional speed sensor. However, the rotational speed can also be entered manually. The new route point can now be saved. It will appear in the route table. Now let's create another route point. If you select an existing route point before detecting a new NFC tag, its data will be transferred. This may make it easier to enter the data. The table now contains 2 route points. Let's take the first measurement. To do this, move the device closer to one of the NFC tags. The corresponding route point is activated, and the measurement button can be pressed. The measurement screen displays a set of overall values and graphs for the selected mode, in this case the measurement of vibration values for unbalance monitoring. The measurement is triaxial. On the left, you will find the 3 overall values with the selected filtering and integration. If these exceed the specified warning or alarm threshold, this is indicated by corresponding icons. Below these are the measured phase angles. Observing the phase angles over a longer period of time can help to detect changes in the machine condition. The short-term trend provides information about the stability and plausibility of the measured overall values. Average values and variances are displayed. The spectral representation of the measured vibration in the range from 3 to 300 Hz can help to assign vibrations to specific components of the machine. The 6 largest amplitudes and their frequencies are displayed. The measured or entered speed is shown at the top right. The purpose of route-based measurement is to record trends over a longer period of time in order to detect changes of the machine condition. Pressing the CSV button saves the displayed measured values on SD card. The trend button next to the overall values opens a time diagram showing the history of the values measured so far. The warning and alarm limits are also displayed. A trend diagram is also available for the phase values. Now we take a look at the functions for roller bearing monitoring. To do this, we create a new measuring point. This time, we select bearing vibration. The measurement is performed on a single channel. Sensor channel Z is selected. Warning and alarm limits for overall values also need to be entered for bearing vibration. We press the measurement button. The measurement screen shows a set of overall values and graphs tailored to roller bearing diagnosis. Roller bearings primarily generate higher frequency vibrations. Acceleration is suitable for this purpose. It is displayed as RMS value, peak value, and crest factor. Progressive bearing damage and the resulting micro-shock pulses would manifest themselves in an increase in the peak value compared to the RMS value, corresponding to a higher crest factor. For stability and plausibility checks, the peak value is displayed as a short-term trend. The envelope spectrum is also displayed. If the bearing geometry is known, conclusions can be drawn about the damaged component of the bearing. The highest amplitudes of the envelope spectrum are also displayed in tabular form. The spectral distribution of the acceleration signal provides another tool for damage assessment. As damage progresses, conclusions can be drawn from the trend of these measured values. The more severe the damage, the more the damage frequencies shift toward lower frequencies. Finally, the rotation speed is also measured. Pressing the CSV button saves the displayed measured values to the SD card. Trend graphs can be shown for peak value, RMS, and crest factor. Let's take another look at the root point table. The measurement points in the root table change color depending on whether the last measurement is still within, just outside, or significantly outside the specified measurement interval. Points with a black background have not yet been measured. This allows you to see at a glance which measurements are overdue. Now that we have looked at the module for route-based machine monitoring, let's take a look at the envelope analysis module. Envelope analysis is a tool for roller bearing diagnosis. A bearing, consisting of an outer race, inner race, rolling elements, and cage, generates certain characteristic rollover frequencies during rotation, which are in a fixed ratio to the rotor speed, specified by the design. An increased spectral amplitude at one of these characteristic frequencies allows conclusions to be drawn about damage. With a simple FFT analysis, it is hardly possible to extract the relatively weak rollover pulses from the vibration spectrum of a bearing. Envelope analysis has proven to be effective for this purpose. Bandpass filtering and fast peak detection are used to form the envelope of the acceleration signal, which is then subjected to an FFT. Depending on the degree of damage, the following characteristic frequencies clearly emerge from the envelope spectrum: the ball passing frequency inner race BPFI, the ball passing frequency outer race BPFO, ball spin frequency BSF, and fundamental train frequency of the cage FTF. Rotation speed dependent markers are set at these frequencies to characterize the selected roller bearing. Markers with clearly prominent spectral amplitudes indicate damage. In the example shown, this is particularly the case with BPFI, which indicates inner race damage. By comparing measurements over a longer period of time, the progression of the damage can be examined. Here we see the setup menu. The envelope analysis is performed on a single channel. The sensor axis can be selected. A variable high-pass filter can be used to attenuate low-frequency vibrations from other sources. The gain is usually selected automatically. In the case of fluctuating signals, several spectra can be averaged to obtain more stable results. The rotation speed required for evaluation can be measured with the optional RPM sensor or specified as a fixed value. Here, the four bearing factors are entered. They determine the marker positions if they are multiplied by the rotational frequency. The factors can be calculated from the data published by roller bearing manufacturers or taken from pre-calculated tables. Finally, we will take a look at the amplitude over RPM module, which is also included in the machine monitoring software license. It displays the amplitude of up to 9 signals as a function of the measured rotation speed. Applications include run-up and coast-down tests and detecting resonances. It is possible to specify whether only increasing, only decreasing, or RPM changes in both directions are recorded. The resolution is determined by how quickly the rotation speed changes. Up to 9 RMS values can be displayed over the rotation speed. These can be different RPM values from the same sensor signal or, in the case of the VM100A, up to 9 different input signals. Single or double integration, high-pass, and low-pass filtering can be selected individually. The maximum rotation speed is 60,000 revolutions per minute.